Yes, we can hear you clearly.
Okay, great. So welcome everyone to this webinar and good evening, afternoon, and morning to everyone. Let me just take a quick poll before we get started. How many, if you can just indicate where you're joining us from, uh, mainly India and Asia, Europe and North America. Uh, can you should be able to see a poll in your webinar. Can you expand that option? Uh, Vivek, are you able to see my screen?
The poll is not visible to me. Is it visible to others? Poll is not visible. Sunil, you have to launch the poll. I think you have to
Got it,
select the
got it.
poll.
Yes, you're right. I just, yeah. Can can everyone see? Yes, select the poll now. Okay, I see people are entering it. Great. I'll give a few seconds. And pardon my voice, I'm running a bit of a cold. So, if there is an interruption, excuse me for that.
Yes, Sunil, you can see a question mark popping up sometimes below the controls. That's your chat window where somebody is trying to ask a question. If
Okay,
you
great.
click on,
Yep, I can see that, and I see that everybody. So we have predominantly mostly from India, and a few from Europe and North America. So great, welcome everyone. Uh, so our topic today, and oh, I'm calling in from Bangalore now. So okay, I'm just going to close it now. Okay, tell me if everyone, Vivek, I'll just use you as as my test audience. You can see my screen.
no, you have to show a screen. There is under sharing, there is an option called show screen.
Um, let's see. The last time I got that prompt, Vivek, on my screen. Uh,
Okay, one sec. Let me try something here.
yeah,
Hold
this
on.
I didn't see the prompt, so I thought maybe it was already.
Yes, so sorry.
Yeah,
Now you can show the screen under
I can.
sharing. Yes, we can see your screen now. Yes.
Okay, perfect. So the agenda, we have a fairly busy, next 50 odd minutes. So I'm going to briefly run through. I will talk about, at a very high level, what is the significance of business forecast. I think some of it is very intuitive, but it might just help to give some more context. We'll do a fair amount of deep dive into different forecasting techniques, and then get into the application of AI in forecasting, and then conclude that with some key takeaways. And we keep it very interactive. So throughout the session, as you have questions, please um, put that in the on your webinar screen, and we'll try to address it. Okay, so forecasting in daily life. Before we get into the context of a business forecast, I think just to set the stage, we do forecasting pretty much on a daily basis. We just don't see it that way or call it that way. But if you look at the food we order, it's based on a certain expectation of consumption pattern or demand. We all look at weather forecasts. We do travel forecasting, or at least travel time estimation. And of course, there's always some kind of a budget forecast that happens. So it's something that it's almost second nature to us. But then, when we talk about business forecast, there is a little more structure that we have to start applying. So let's look at what are the different types of business forecasts that we might do in our profession. We have the most common one, which is projecting demand. And typically demand has two components. There is a volume and a price. Uh, Volume is sort of the most organic piece of demand. Then you get into price. If you have that as a variable. We also do forecasting of what is the supply that will come to meet that demand. We have project scheduling, which again, is some kind of a forecast that we generate based on the expectation of how much time it takes to complete a certain set of tasks. We have capital expenses, which has to be forecasted. Human resource staffing needs, very common forecasting exercise. Budgeting, again, very typical. And then cash flow, even which is a little bit different from the budgeting step. So, I'm sure you have been involved in some forecasting exercises. You look at this spectrum of different activities. Now, just another quick poll as you look at what you do in your job. Can you respond, and let me just open this very quickly as another poll. How many of you have done any kind of forecasting in your profession? So I'll give a few more seconds. Okay, good. Looks like we have almost a two-thirds of our participants, or maybe 60 to 40. 60% have done it, and 40 may have not, which is a very typical mix. But it's good. At least as a baseline, we know that many of you have been involved in some kind of forecasting. So moving along, I'm just going to close this now. And thank you for the quick responses. So as we look at, and I'm just going to close this screen. Vivek, if you wouldn't mind, I'll minimize so that my screen can be visible to everyone. If there is a question that comes up, just interrupt me, please, because I may not be able to see my screen.
Sure,
Okay.
I'll check the questions and let you know.
So, what is the typical, business challenge around forecasting? It drives a lot of decision making. Obviously, we looked at many of these examples, and they are all they drive some critical business decisions. But why is it important, and what is the challenge? Forecasting is this delicate balance. That's what I try to capture in this visual. You cannot be, over forecasting because that has consequences. It can lead to excess capacity if you forecast it demand to be a lot more than what it actually comes out to be. It can lead to high inventory. It can lead to write-offs. It can lead, in some cases, to shutdowns. One example is, I don't know if you know of a product called Segway. This was this automatic scooter, and when the product was being launched, the forecast that they generated were so much higher than what the actual demand came out to be, that it resulted in plant closures. Under forecasting also has negative consequences. And the obvious one is, if you did not predict the demand well, it can lead to stock outs, lost sales opportunities. It can surely impact your customer service or even the reputation, especially when you are serving a very critical consumer. So, it's very important to get to the optimum. You can never get to the most accurate one, but what this is trying to highlight is it's a balancing act. Typical forecasting accuracy is a very simple, we call this an equation, but it's a very simple. You just take the difference between the forecast versus the actual, but then you take it in an absolute term, because as we just saw, both over and under can be a problem. And then, you take that as a ratio of the actual demand, and then, based on the differential, the accuracy is calculated as a percentage.
Yeah, hi Sunil.
Yeah.
Your voice is breaking up a couple of times.
Okay. Let me see. I can make sure. Is this better?
Yeah, you are using a speakerphone, right?
Yes, I am on a headset with a speaker.
There is some background noise. I don't know what it is.
Um, maybe there is some tie of mine. How is this? Is it better?
No, it is. There is some kind of background noise. I'm not sure.
Okay. Let me switch my headset.
Yeah, try a
Apologies.
different headset, perhaps.
Yeah, apologies. One is let me.
Yeah, we'll let Sunil, find a different headset. Maybe there's some headset causing background noise.
Is this better?
Yes, yes, this is better.
This is better. Good. Sorry about that. Okay. So one last polling question. For the 60% who says that they have done some kind of forecasting, uh, what I would like to know is, do you calculate your accuracy, and typically what is your accuracy? Now, given three options: under 50%, between 50 to 80%, and above 80%. Okay, it looks like almost, surely a majority of them have an accuracy above 50%, which is really good. This is quite impressive, actually, because the norm is forecast accuracy does not come out to be that good. So actually, you're already above average. So it's a good audience to talk to. Okay, thank you. Okay. So if you look at very quickly the evolution of forecast, and I'm using an example of a navigation system. Until the 18th century, we only had this compass, and in the 18th century, and going all the way into the 19th century, we started using maps. This was a way to estimate and how to get to a place, and in some cases, and I don't know how they were estimating how long it would take, but I'm sure that was part of the approach. Now, interestingly, in the 20th century, nothing really changed. Only the quality of paper. So you look at, this is the map of New York, which is taken from sometime in the 19th century, and this is a more recent map. The quality has changed, but the approach has not changed. So until pretty much the end of the 20th century, there was not much happening. Now, you get into the early part of this century, and we started getting into the GPS. Now we have a more, what I would call as a more quantitative approach to arriving at the expected time. Again, this is to forecast how long it might take you to get to a certain place. But that still wasn't enough. And what we have today is, a very data oriented way to forecast how long it will take me to get to it. And that's based on using the live traffic update, which I'm sure most of you, if not all, have used at some point. Now, this just happened in the last, at least what I remember is about 3 to 4 years ago, we started seeing these traffic uh, lights in our GPS. So you can see that we have moved well, it was gradually until, the early part of the century, but now it's a very rapid migration to very quantitative approach to forecast. And, who knows what's coming next? I'm sure there are people working on even better approaches. The point of this is forecasting techniques, as we saw in that example, can be of two types: qualitative, which is mostly around gathering input as opinions, as judgment, estimates, historical analogs. If you didn't have any actual relevant data around a specific product or some other exercise that you're doing, you will look for some valid comparison. Now, that technique, and I see that I've missed this animation, went a little bit out of order, but when you don't have data, this is the only tool you can use. And this is generally appropriate for new products where you may not have a past history or long-range decisions that you might make. Quantitative approach is what impacts business decisions on a daily basis. And I'll walk through each of these at a very high level, but the progression here is as you get more and more data, your approach to forecasting becomes more and more robust. You start with naive, which, as the word says, is the most naive approach. You get to an average, then it is about trend analysis, you get into multivariate analysis, and then something which is now the cutting edge is the use of neural networks for forecasting. This obviously relies on availability of good data, both in terms of the volume and quality. This is with the premise that the past performance is a good predictor of the future. If you go back to the GPS example, the fact that you have other drivers who are using the same Google Maps, and they're driving either slow or at the regular speed, is the predictor of how much time it will take you. So that is the key premise. And the data, the good thing is, as you get more and more of the data available, that will help you only get better and better by refining and revising the forecast. So let's look at each of these approaches. The naive approach, as the word suggests, this is used when you are at the beginning of any forecasting exercise, when the data is very limited, as limited as you may only have one data point. And the approach is very simple. It's the forecast that you will generate for the next time point is effectively the same as the previous pattern. So you can start with n equals 1. You don't need a whole lot of data. It definitely has shortcomings, but this is the best you can do. And you'll see that we started with literally only one known data point. And as we progress through this session, you will hopefully see this getting richer and more complicated and more relevant to real life. So we have the blue is the actual, the data which was 153 in this case, and the prediction is the same, 153. Now you have started getting more and more data, and then you move to the average, which again builds on, earlier we only had one blue data point, and now we have, let's say, 3. So if this was monthly, we now have at least 3 months worth of data. At least one approach you can take here is use the average. So the average of these three data points is 150, and that is what you would carry as a prediction for the next time. You could, because with three, there is a temptation that you can try to draw some trend. Now let's see what that does. So I've tried to draw trends, and it is taking me in a certain direction. It's basically showing that there is a negative trend over time, just with these three data points. Now, there is, and you'll see as this data set progresses, there is a risk. So you have to be cautious when you're applying the trend with very limited. And that is effectively, so the point here is for trend analysis, for you to transition from average trend analysis, you want to make sure that you have enough data with you, because otherwise it can lead to misleading outcomes. So as more data becomes available, so this is your example. So it's the same data set, but now instead of 3, you have 12 data points. And you can see this is a lot richer in terms of data to allow you to draw some trends. The earlier data set was too small. It turns out that the average of this data set is 151, and the trend line, which is pure regression fit, which you can do. And this is, by the way, a lot of this analysis was generated. So this is something that you can do very well without having to. My screen is still visible, right? Okay. I'm assuming that everybody is seeing. So the
Yeah, hi,
average.
Sunil. I think your headphone is acting up, so it is creating some background noise. One idea is you can speak directly in the computer or try a different headphone.
Oh, so this one is also now starting to act.
Yeah, it is creating some background noise for some reason. You can try speaking directly in the computer if you're in a silent room.
Okay, let me try that. Can everyone hear me? I've removed my headset now. I'm speaking straight to my laptop's microphone.
Yeah, we can hear you, but the noise is still there. So I think it's not the headset per se then. It is something else. So I guess you can put back the headset.
Okay. Yeah, I'm
Somebody is
back on my.
suggesting it's a Wi-Fi network. So, but that's okay. We can't do much about it. You can try the headset again.
Okay. I just switch my right and left ears instead of just trying anything different. Is this better?
So there is some background noise. So uh, I think the Wi-Fi is a problem which we can't do much about. So you can just continue with the headset. Okay.
Okay. Okay, fine. So in this example, you have the average as well as the trend line giving you similar values. Average is about 151. The trend line is basically saying that this is a relatively flat profile, and the value would be, this is the value of that equation, and it will give you about 158, 148 plus a small dependency on x. Now, another thing to note, and I'm getting a little bit into statistics just to give some more context. The typical coefficient of correlation, which is showing you how correlated your output is to the input, is giving a very low number. So the R square, the closer the R square is to 1, the better is that correlation. So this is telling you that the value of this output is not getting much influence by the input, which makes sense. We can see that visually as well. So that's why the average and the trend line are giving you very similar values. Now, so what you see is now you have the full data set. So earlier it was only 12 points, and now we are building this data set to now show 4 years worth of data. So these are effectively 48 group points, 48 monthly data points. Again, the trend has not changed. It's still relatively independent of the time, which is your x-axis. There are some other things that were worth noting. Besides the average value, which is projected by this red line, we see that this was the actual data, the red boxes that you see. Is the actual data for the duration for which we generated the forecast. And there's obviously some scatter. Now, what you see is by putting the confidence interval, and that's another statistical parameter that you will get when you run these regression fits. You can get the upper limit and the lower limit. The confidence limits can be any value generally in the 90%, but 95% is a very typical value. What that does is, if you know that this is the profile of the data, and you want to cover any movements above and below the projected value, you can at least get a good confidence of what will be the range within which the values that we are forecasting the actual will come out. So that's one technique to be able to estimate the boundaries of variation. The other thing that you see here is, again, R square, the coefficient of correlation, is not very well correlated to the time series, which again tells you that this is really a flat. Now, this is a different profile. You clearly see that there is a trend here with time. And if you were to take an average, would that work? Probably in a certain time frame it might. If you did not, let's say we were to do this in the same way that we did the previous exercise with 12 data points, you might see that this is flat. But that again would be misleading. And so this is again highlighting the value of having enough data to run any of these more data-rich analysis. So the average would have been 298 in this case, but that clearly would not reflect what you should be forecasting. To generate the forecast, you would run a trend line, like we did in the previous exercise. This time, the trend line actually shows a dependency for the output to the input value, and that can be visually seen very clearly. And you can also see that in this R square value, because now it's much closer to 1. It's not very.
What is R square?
So
what is
R
R square?
Is that, yeah. So if you can hear me, R square is the coefficient of correlation. What that is telling you is how strongly is your output, which is the Y, let's call the Y-axis here as your output. How strongly is that correlated to your input, which is the X-axis? In the previous example, even though the trend was a straight line, there was no correlation between the input variable X and the output one, because it was flat. Let's say the slope was practically zero. Does that answer?
Yeah, thank you.
Now here you also see that the scatter of the data is a lot more compared to the previous exercise. And this was the projection based on this trend. So the red line was the trend that gave the projection, which is the green, solid green line. And we calculated the upper and the lower bound, 95% confidence interval. But look at what you see. You generally would hope that the 95% upper and lower limit would cover the all of these variations. But in this case, it does not. There is one outlier which fell outside this 95% limit. What that tells you is looking at the trend, you know, looking at the trend line just from the slope is not enough. You have to look at the scatter too. Because if the scatter is a lot, then sometimes in this case, even the upper and lower boundaries are not going to be enough to tell you that your forecast would cover all of the possible. So, the message here is know the variation in your data. Besides, now this is, so you can see that we are gradually increasing the complexity. This is a slightly different case where you see the values, and these are, by the way, real data. You see that the values reach a peak at a certain time and the trough, the bottom at certain times, and they repeat themselves. And this is clearly repeating every 12 months. So, what is telling you is there is definitely a pattern which reflects some seasonality. And seasonality is something that practically at least every product forecast will have some element of seasonality. You can think of, whether it's a consumer good, which are driven more by the peak season, the holiday season, or a medical product, or even automobiles and anything else. So how do you handle, so here the pattern is recurring every 12 months. So there are two methods. There is a recurring pattern, and the frequency or the duration of recurrence is every 12 months. How do we handle seasonality? This requires a little bit more data processing. So earlier we just took the raw data and we tried to apply the trend, and then we did the regression and looked at what is the fit. Because of seasonality, you could take that same approach, but you would lead to a false conclusion that there is a lot of variation, when in fact it's a predictable pattern. This is not just random variation. To handle such kind of seasonal data, we have a multi-step process. Step one is you first have to de-seasonalize. Now I'll show you what we mean by that in a minute. We then use the same kind of regression analysis that was done in the previous cases. That is done to establish the trend. After we know what the trend is, we apply a seasonal index. So effectively, it's re-seasonalized. In step one, we de-seasonalize. But now to generate a valid forecast, we have to re-seasonalize that data. And once we get that seasonal index, we generate the actual season. So let's see what we actually mean by that, these steps. So this is the data that we just saw. Now, the first step is, because there is a recurring pattern, we need to first look at what is the moving, what we call as, there are multiple ways of normalizing this data. We need to normalize this data because that is the only way we can get it in a form that can help us to generate a trend. One way to normalize this is run a moving average. The moving average is run over the duration of the recurring pattern. In this case, it was 12 months. So the first moving average would be the first 12 months. The next moving average would be month 12, month 2 to 13. The next one will be month 3 to 14, and so on. What that does is what you see on the left has now been transformed into a much easier profile to perform trend analysis. So the right chart is the same data that you saw, that you have on the left, but it has now been normalized by the use of moving average. Now, once you have this form, and this will typically be a lot smoother. The reason is you have you have a collection of 12 points, and they repeat. So the first moving average and the second moving average have 5 points in common, or sorry, 11 points in common. If you look at that shifting average, so that's why this is always going to be a lot smoother. And you can then look at the trend. In this case, it looks like a flat line. And since it's a flat line, you can apply the average approach. You also see that the R square value again is very low, which tells you that it is fairly independent of the times. It is seasonal. So the distinction you have to make here is the seasonality is there, but it recurs itself every period. So the period here is 12 months. And hence, over a long cycle, it is relatively independent in terms of the moving average. So that was step 2. So we did the deseasonalizing or normalizing of the data, and then we ran the regression on that deseasonalizing. Step 3, and this can be a little complicated, so I'm going to take some more time. What you have is this is the raw data for the first 12 months. These were the numbers of demand from month 1 to 12, and you calculate the average. What the seasonal index, because you've determined now that the seasonal pattern occurs every 12 months, the seasonal index is really the ratio of that month's demand to the average demand for that year. So that's how you get the seasonal index for every month of the year. Now, because you had 4 years worth of data, and you know that this is a flat, which means that it was repeating itself every year. You just want to make sure that you take the average of the 4 years. You could have just stayed with the seasonal index relying on year 1, but that would have meant that you did not utilize the full power of the year. So what this is doing is, from year 1 to year 4, from year 1 to year 4, you are generating the values in the same way, and then you're getting the average seasonal index. So coming back, this was the seasonal index value for the first year. You added the other 3 years using the same approach, and then you're generating the average values. So this gives you the average seasonal index for the month of January. Let's say one was Jan, and February and March and so on. So that is now allowing you, what you're doing is now you're knowing exactly what is this variation pattern across the 12 months. And you apply that pattern to your forecast. And what you see here is the green line is the forecast that you got by applying that trend, applying this seasonal index. And it turns out that it's actually not a bad fit. So the red boxes is the actual data. You'll never get a perfect, but this at least gets you a good way to handle it. The next profile is very similar to what we saw earlier. It again has a seasonal pattern. The only additional piece here is you also now have the earlier example, the deseasonalized trend was flat, meaning it did not change the time. But in this case, there is actually some growth happening. So, the approach doesn't change. You just have to know that now you have to factor the growth when you do the forecast. So you can then see that this green dotted line is the forecast, and the red, in this case, the red triangle was the actual. So again, it's not a perfect fit, but it's a pretty good indication. Let me stop here before I get to the next. Any questions? Am I audible?
Yeah, you are audible. So if you have any questions, you can ask them now before we proceed further. Yeah, there was a question. Let me just put it to your attention. One sec. So how do we tackle outliers in trend analysis?
So what you really, so if I'm let me go back to the trend analysis. Is the question about this outlier?
Yeah, perhaps.
So there are, so this outlier, because it was a forecasting exercise, you know the only thing you can do is if you know the variation is very high, you may decide to use a 99% confidence interval just to be very sure. Now, you know, as you broaden the confidence interval, you have to keep in mind that, you know, so if you look at this, you have a lot of the actual values fell below the mean. This space is free and so whatever is the business cost of carrying a wider range, you have to factor that into your decision. But one way to handle the outlier is, at least to cover this, you will have to increase the confidence. Hope, hope that answers.
Yeah, fair enough. So no further questions right now. You can proceed perhaps.
Okay. So I'm looking at the time. We have about 15 more minutes. So let me keep it up. Multivariate planning. So up till now, what we were looking at is one independent variable, which was the time scale, and one output or dependent variable. So one x and one y. And those are your typical time series plots. With multivariate, those are actually the more real life examples that you will come across. And let's look at this one example. So what we have, it's a very small data set. It's a commercial property. It has four different variables, the independent variables, x1, x2, x3, x4, and they impact the value of that property, which is the output. In this case, they are trying to, this is all the assessed value, and we want to get a projection of some additional properties which is shown in the red. Now, in typical machine learning approaches, you would call this as the training data, and this would be your testing. It's a small data set, but the model gets built by using your training data. We're not getting into the details of that approach, but in this particular example, let's look at if you were to plot each of these independent variables uh, against your output y, you'll see these four plots. The top one is y versus x1, y versus x2, y versus x3, and x4. While you can get some trend, there is no clear insight that you can derive. Look at the R squared. Here it says this is pretty much independent of x for these two, x1 and x2. And here again you have some dependence, but there is no you could derive some conclusion, but uh, it would not be very insightful. And that's why, you know, in a multivariate situation, just a visual analysis of a single variable is not going to be enough. What you have to do is, just like we ran a linear regression on a single variable, you can do that for a multivariate set. And this can be actually done in Excel. There is a linus function which can take one or multiple independent. And you, with any regression, it uses the least square approach, and it will apply a very typical equation because it's a linear regression. It will apply the, the, the power of each variable would be one. So you'll see y equal to m1x1, m2x2, and so on for any number of variables that you have. Now, obviously, this becomes challenging to show visually because you have multiple dimensions. But what you can use very effectively are the statistics that come out from this, from the use of this function. And they give you the coefficients of the fit, so you get the m1, m2, and the p-value, which you can see here. You also get the standard error. So when you have to estimate that 95% confidence, you can get the output of the standard error, and then the coefficient. This is the overall coefficient for it. What you see here, and this is a very typical way to show the validity of your prediction. Because you have multiple x values, you cannot really show all the x's versus a given one. What you're showing here is the actual value of, so in our example, it was the assessed value of that commercial property versus the predicted value. The blue is the model based on, blue are the actual data points, the training data that was used to generate this, and the red is the evaluation data or the test. You can see that the blue fit is very strong. The red fit is not as strong, but it is, given that you have multiple variables, it is as good of a fit that you can from the data set available. And mind you, this is a very small data set. So as the data becomes richer, you should be able to get a much stronger by using this. And you can see that unlike what we saw with each of these independent variables, the values that you're getting here are very different because you have the merger of 4 different variables impacting the prediction. Okay, so the last piece, and given that we have limited time, I'm just going to touch upon this at a very high level. So far, all of the approaches that we looked at, we told the system how to predict. And what I mean by that is, we were, excuse me, we were guiding the regression by saying this has to be a linear fit. And we use our judgment based on the visual analysis. So it was kind of a guided approach. Now, in many situations, what we have is, and I see that I'll touch upon this slide in a few minutes, but let me just walk you through the concept of artificial neural network. So our example so far, we were mainly looking for the best fit. So what we were exploring were the coefficients. We had a predefined relationship. We said that they are linear, again, based on the visual analysis. But many a time, when we have a large amount of data, we may not know what that underlying relationship is. And that's where we get into the concept of using neural networks. A real neural network is what actually works in our brain. And, as we grow from an infant to a toddler to a child to a grown-up, we stimulate so much information, and we recognize, there are patterns or there are some benchmarks, and that helps us to make, improve our learning. In a very similar way, when we have neural networks in an artificial setting, which is using machine learning, you are essentially trying to simulate the ability, the way that the brain teaches us to simulate that in an artificial setting. So that is the concept of an artificial neural network. Now, we obviously don't have the time to get into the technical details, but this is just to give you some from high level background. And what an ANN does is it starts with the input and the output, and it has to now figure out how do I develop a learning process which helps me to project the output given the set of inputs. And the way it does that is it introduces what we call as hidden limits. So let's look at an actual example. And this is a very well-published data set. The city of Boston, they were trying to do some assessment of what influences the housing crisis. And they picked up a set of totally unrelated input variables. You have the crime rate, some zoning parameters, which is driven by the local government, the proportion of retail versus non-retail businesses, the proximity to Charles River, which divides Boston from Cambridge, the pollution level, the number of rooms, the number of rooms in a house is probably what you would see as the most immediate or the most relevant variable impacting the cost of house. But they picked up many different factors, 13 variables in this case. And actually, there's no predictive way of telling, the crime rate will impact the housing price, let's say in a linear or in a polynomial. Right? I'm just using that as an example. So how do we do that projection? In this case, the ANN process was applied. You have the 13 variables as input, and you had the output, which is the median value of the house. There are two sort of competing analytics that work within a neural net. You have what is called as a feed forward. The input variables get processed, and to allow the processing to happen, you have to sort of reduce the number of nodes, the complexity that you would have the system working. And so essentially the forward approach is about some orientation, some combination of these different variables with the objective of fine-tuning to get to this output for every data point. In this data set, they had about 500 data points. The back propagation is the learning and revision. So think about if for a child, if you were to keep, they do, and they always like to do something which they are told not to. But if you tell them that this is wrong, over time, that training gets engaged. The back propagation is essentially that same message, this is wrong, being said in a programmatic manner, in an algorithmic manner. And that back propagation, the intent is to keep checking the error and reducing the error, so that over a set of iterations, the nodes have learned enough to reduce the error and get you as close to the actual value as possible. Now, I know I'm saying this in very non-technical language, but this is just to give you the idea of how the ANN would operate. The black line is the forward move, and the blue line is the bias, which is known once you reach the node and you get the back propagation. With that, we come back to this kind of plot that we've seen before, actual versus predicted. You see that it is a reasonably good fit. Now, with 13 variables, we cannot expect a perfect match, everything lining up on one. But this at least tells, and this was run with real data. That as a concept, this can actually work. You can see that ideally y should be equal to x, which means that the prediction is the same as actual. It's pretty close. It's 0.97x. And the coefficient, the correlation, the dependency is also quite high. So, it tells you that at least as an exercise, this gave us enough so that next time we have some model to do the prediction. So let me wrap this up. We started with very small, in fact, just one data point, and we kept expanding and increasing the complexity. The core message, if there's one takeaway, I would like you to take from this is, knowing that the ability for data to be leveraged in a very effective way. As you get more and more data, you can do a lot more in forecasting is one key message. And then you can apply machine learning techniques. We saw, the earlier examples are simple enough that we could have Excel handle it, but as we progress, it would require some more computing intensive approaches. Once this is done, if you think about those upper and lower bands, if you were to say, I am covered with my forecasting, I'm covered up for my 95% upper and lower limits, then your business management can be done more by exception. So we talked about this outlier. Let's say the outlier was not covered in your upper and lower bands. You just have to handle those outliers. But everything else becomes more business as usual. You can apply the learning that you get from an existing exercise or a product to a new one where you have no data. And hopefully this can all lead to an improvement in business. So my apologies, I ran just a minute over, but I want to make sure that we have at least a few minutes to take some questions. Thank you, everyone.
Yeah, thank you, Sunil. Any questions? You can ask them now through the questions or chat window. So any questions? Final call?
Okay. If not,
okay, I guess there are no questions. One sec, just a moment. Yeah, no questions. All good so far.
okay, great. Thank you, everyone. Have a good night, a good evening, and a good day ahead for all the folks in different times.
Thank you, Sunil.